Here we present a method to retrieve the parameter of an elastoplastic fracture mechanics model from experimental and numerical methods. These are the outline of my presentation. I will start with a brief introduction of the topic. Then I will describe the experimental test we carry out in our laboratory. Then the computational model we implement. And after that, the parameter identification procedure, and finally some conclusions. So, in order to describe ductile fracture, it is very common to use Constitutive model. Constitutive model is a traction separation law, and the main problem of this law is that the parameter that describe the curve cannot be retrieved directly from experimentation. So they have to be retrieved in an indirect way. Some methods are the minimization of a potential function that measure the distance between the experimental result and the numerical simulation, or for a differentiation of the J-integral. We apply the theory to a material that is made by the busbar. Busbar are the metallic strip that electrically connect photovoltaic cell. This strip can suffer tensile stress and fatigue due to the thermal excursion. In fact, it is studied that that gap can increase of about 60 micrometer, that is a 3% strain. So the experiment we carry out, we take pieces of busbar that are made of copper coated by silver, and we put inside a scanning electron microscope and perform tensile test with notched and unnotched specimen under displacement control. These are the results that we get. The black curve is the unnotched specimen, where we have a clear elastoplastic behavior with hardening. And indeed, the blue curve and the red one are the two different notched specimens in which we have elastic behavior that is overcome by hardening behavior. So plasticity is development, and then a softening behavior when the cracks start to propagate. That interpretation is confirmed by the microscopic images. In fact, in the first top left image, we can see the notch tip during the elastic range. Then, as to bear a strong plastic deformation, and after that, the cracks start to propagate until the final failure, where the crack persists, right? This is the computational model that we implement inside the final element program FIP from the Taylor. We use quadrilateral element to describe the bulk material, and for now the interface element with the formulation of particles for the crack behavior, the cracked part. That is that blue one, the darker blue. The constitutive model we implement were a bilinear elastoplastic model for the bulk, where the parameter that has to be identified are the Young modulus E, the yield stress sigma y, and the hardening parameter H. And for the constitutive model, we use the Berger model, that is a third degree polynomial that is identified by two parameters, the maximum tensile stress sigma max, and the critical opening DC, that are respectively that peak point and that final point. First, we identify the elastoplastic parameter interpolating with a bilinear curve, the unnotched specimen curve, the notched specimen results. Indeed, for the identification of the constitutive model, we had to perform many simulations and try to identify them manually. Finally, we get that best fit for the first displacement curve of the 0.45 millimeter notched test with a parameter of sigma max of 6.5 megapascal, that is around twice of the sigma yield, so it's an acceptable value, and a critical opening of 0.5 millimeter, that is not really acceptable because it's at least 3 order of magnitude of the real value. In fact, if we use the same parameter to try to fit another notched specimen of 0.8 millimeter, we match the first part where we get the elastic stiffness and the maximum force, but we totally mismatch the softening part. Then we propose to use an enhanced coefficient model that depends on 4 parameters instead of 2. That parameters are the maximum tensile stress and the critical opening, like in the Berger model, plus the initial stiffness of the curve, K, and the separation corresponding to the maximum traction, Gm. We end up with a 5-order degree polynomial in which the Berger model is included. In that way, we want to have more control on the shape of the coefficient model than on the fracture energy. We perform a preliminary sensitive analysis of the coefficient model with respect to the 3 parameters, keeping constant 3 parameters and modifying 1. So, for example, if we modify the initial stiffness by 3%, we get an increase in fracture energy that is more than 10%. Indeed, if we modify the critical opening of about 70%, we achieve an increase in fracture energy of about 30%. So the derivation of this parameter cannot be carried out manually. So we implement in MATFIP, that is a MATLAB interface for FIP, an optimization algorithm. We use a gradient descent method with backtracking line search. In the gradient descent method, we look for the optimum of the cost function following the negative gradient. More in detail, we collect the 3 parameters in the G vector and a generic optimization loop N. Start with the computation of the cost of the current parameter, then we compute the numerical derivative with a central difference approximation, and then we have to choose the step length with the backtracking line search. In the backtracking line search, we start the step length t with a value t0 that usually is 1, and we decrease it of a factor beta every time that the backtracking condition is not satisfied. That condition will be satisfied when the cost function of the current line search increment m is less than the linear extrapolation of the cost function. We also add in the backtracking line search the constraint on the domain of the 3 parameter with an if statement. After that, we exit with the step length, and we can compute the parameter at the next optimization step as the current parameter minus the step length times the gradient. We finish the optimization procedure when the error that is the norm of the gradient is less than a tolerance. We try to test the optimization algorithm, try to derive some parameter that we already know, that were the elastoplastic parameter. In this tree graph, the elastoplastic parameter are the Young modulus, the stress, and the hardening. And in this tree graph, you can see the evolution of every parameter at each optimization step. In that last bottom right, you can see the fitting result of the simulation with respect to the experimental test, taking into account the last converged parameter. So we first use the method as I described before, and the results are depicted in blue. We have a very good agreement in the yield stress and in the hardening parameter, but we totally mismatch the Young modulus. So we enhanced the algorithm in introducing some weight that gave more importance to the elastic part of the simulation, and we achieved a very good agreement in all the 3 parameters. Then finally we propose to use the same optimization procedure to retrieve the coefficient model parameter. In that case, the cost function should be another one, and we think on using a cost function that depends on a micro part and on a macro part. The micro part could depend on, for example, on the crack opening mouth, and the macro part on the force and the displacement. We can weigh them in order to retrieve at which scale has more important diffraction. Also, it has to be a constrained optimization problem in order to avoid and physical results. In conclusion, tensor tests have been carried out on silver-coated copper conductors inside a scanning electron microscope. The elastoplastic constitutive parameter have been identified with a standard procedure, which provides a good agreement with experimental results. The identification of the Constitutive model parameter is more problematic, especially to match the micro and the macro response at the same time. A 4-parameter Constitutive model has been proposed to improve fitting between experimental results and numerical prediction at the micron and micro scale. Parameter identification cannot be carried out manually. A constraint optimization algorithm is required. Finally, I would like to acknowledge the European Research Council to give us the funding for our research.